So I'm going to speak indeed on some recent progress on groups of area-preserving homeos. Not so recent, in fact, it's already 3-4 years old, but I hope it's recent enough. Okay, and it will be based on some joint work with Dan Cristofaro-Gardiner. And Cheuk-Yu Mak, Sobhan Seyfaddini, and Ivan Smith. Okay. And I will talk on these groups of area-preserving homeomorphism, and I will make the presentation. That's the microphone. I will base the presentation on commutators. Okay, so let me start with something which is not on area-preserving homeomorphism first. It's a theorem by Tsuboy from, I think, 2006, which says that every homeomorphism of the two-sphere maybe orientation preserving is a commutator. But in fact, it's not only for the two-sphere, it's for all spheres, but I'm interested in the two-sphere today. Is a commutator. Commutator. Okay.
A means a single?
Yes. Okay. It's really like mind-blowing. Okay, and then the question for me will be whether this holds for area-preserving homeos of the two-sphere. Okay, so question. But maybe that's too much to ask, like to have this for area-preserving homeos. But we will ask maybe less whether like every homeo is a product of commutators. Okay, so whether this group is perfect. So first question maybe is it true that every area preserving homeo of S2 is a product of commutator? It does. Okay. So the meaning is whether this group is perfect. Okay. And the second question we may ask so here it's only one commutator. Okay. And so the question is whether if you take any area preserving homeo, we may ask if we assume it is a product of commutators, then we may ask if there is a bound on the number of commutators needed. Okay. So whether the commutator length is bounded or not. So is there a uniform bond on the number of commutators needed to write an element in the same group. Okay. Okay, so these are the two questions I will be considering. And in fact, it turns out that both have a negative answer. So the first theorem, so it was initially, we proved it with Dan Cristofaro-Gardiner and Sobhan Seyfaddini in 21 maybe. It says that G, the group of area-preserving homeomorphisms of the two-sphere is not perfect, which means that some elements are not product of commutators. Yeah, so that's my first result. Okay. So maybe some remark is that, in fact, what we prove is that this group is not simple. But then there are some ideas that goes back to the 70s and by Epstein, Thurston, and maybe other people, I'm not sure exactly, that allows to show that if it was perfect, then it would be simple. Okay, and so we actually prove. We actually prove it is not simple. So later I will give you some normal subgroup, which is proper. Okay, not simple, and so ideas from the 70s imply non-perfectness. Okay. Okay, so maybe it's a bit surprising, this fact that it is not perfect, because if you modify a little bit the group, like if you go to higher dimension, if you consider volume preserving homomorphism of the sphere with dimension at least 3, then it's known to be simple and perfect, okay, by Fati. If you go to the smooth case, it's known to be simple also by Banyaga. Well, if you remove area, then it's simple also. Yeah, it's perfect. And so yeah, this one is it's like the only one which is like non-perfect. Okay, and now let's move to the second question. So this we proved with everyone. Uh, 21-2. And we proved that the commutator length on the same group so not on the same group, on the subgroup of commutators, okay, is non-bounded. Is not bounded. And in fact, we proved more than that. We proved that it's not bounded in any neighborhood of the identity. In any neighborhood of identity. And in fact, it's not only the commutator length, it is a stable commutator length, which is not bounded in any neighborhood of the identity. Okay. So it means that in any neighborhood of the identity, we may find something which is a product of commutators, but which cannot be, well, I will not manage to finish my sentence. There's no uniform bound on the number of commutators needed to write any element in a neighborhood of the identity. Okay. Okay. In fact, the proof of this result is based on a construction of certain quasimorphisms. So this is based on construction of quasimorphisms. On the group G, which means maps. So there will be a sequence of such maps. Well, maybe I will define what is a quasimorphism. It's a map mu from G to R, such that there exists some constant C, or maybe D, such that for every 2 element Fg in the group, then mu of Fg minus mu of F minus mu of G is less than D. Okay, so this is the definition of a quasimorphism. It's a map like that. If the quantity here were 0, then we would call it a homomorphism. It's not 0, it's just bounded, so we call it a quasimorphism. Okay, and there's a classical fact about quasimorphisms is the fact that it gives a lower bound for the commutator length. I don't know, exercise, you can show that the commutator length of an element f is always at least 1 over d mu of f. Maybe I will assume that all my quasimorphisms are homogeneous to make my life simpler. So I will assume, for me, a quasimorphism will be something that satisfies this and which is also homogeneous. So I assume that mu of fk is equal to k times mu of f for every integer k and every f in the group. Okay. Okay, so I think if you believe in this exercise, you will easily see that when you have constructed quasimorphism, you may hope to have such result that the commutator length is not bounded. Okay. Maybe just to compare some remark on the other existing quasimorphisms. There was an important construction in the smooth case area. This carries quasimorphisms, has all carries the so-called Entov-Polterovich quasimorphism. That's a construction that goes back to 2003 or 4. Okay. But this is based on a symplectic topology tool, because this group can also be seen as the Hamiltonian group of CP1 with the standard symplectic form. Okay. And in fact, they constructed this quasimorphism not only for CP1 but for CPN. So that was one important construction. There were some other construction, but this one will be important for me. Later. And maybe another interesting example, very recent. If we consider the homeomorphism group of any surface of higher genus, I mean by higher I mean at least one, then there is also a quasimorphism, and this is due to Boden, Hensel, and Webb from 1922. Okay. And it induces something non-trivial also in the area preserving case, right? And, okay. And somehow from this example, some of the remaining case was this group G again. Okay. There was no construction of quasimorphism on the group of area preserving homeos so far on the two sphere. Okay. So in fact, these results are based on some tools from symplectic topology, in particular Floer homology. So I will try to give you an idea of what it is. Okay. So some ideas for the proof. So maybe an important first fact is, well, what is written here somehow, the fact that every area preserving diffeomorphism of the sphere is in fact Hamiltonian. What does it mean? So maybe let me write it. So all area preserving diffeos of S2 are Hamiltonian. So what is the meaning of this? It means that they can all be constructed by the following recipe. So we take ht, a function on S2, which depends on t, on time. Okay. And from that, we construct the Hamiltonian vector field, which is just the gradient of ht, but we rotate it by pi over 2. Okay. So it's a rotation by pi over 2 of the gradient of ht. Okay. So the gradient of ht is like orthogonal to the level set. So this one will be tangent to the level set. And if h would not depend on t, then the dynamics would be very simple. It would just follow the level set. Okay? But since we have h which depends on t, you can have complicated dynamics. And in fact, you can recover this way all the area preserving diffeos. So we get an isotopy or a flow that we denote for ht. And so the statement here is that the whole group area is realized in this way. So it's the set of all phi h1 for all such maps. Okay? So that was the first fact. And then the second fact is that when we take the closure of diff, we get the whole group G. So the fact that our group G is the C0 closure, the closure with respect to C0 topology of this. Okay, so it means that we can approximate every element in G by Hamiltonian diffeomorphism. Now I will define for you a subgroup that I will call finite energy homeomorphisms. Sorry? Yeah. Oh yeah, sorry. Thank you. Yeah. Yeah.
About the exercise, I think I know how to do it with 2D, but not.
Yeah. I trust you better than me, so 2D here? Okay. But maybe after homogenization, no. Okay. Okay. So I'm going to define the normal subgroup somehow, okay? So we take psi, an element in G, and we said that it is finite energy, or it has finite energy, I don't know, if there exists some sequence of Hamiltonians. Well, what I call a Hamiltonian is a function like that which depends on time, okay? A sequence of Hamiltonians on the sphere, taking value in R, such that the time one map of these Hamiltonians converge to psi uniformly. Okay, so I don't know if you followed well. If I stop here my definition, then I get the whole G this way, okay? But I don't stop here my definition. Then I will assume furthermore that somehow some kind of C0 norm of the HI is bounded. Okay, so assume that, but it's not exactly a C0 norm, it's a variant of it, which is called the Hofer norm. And we assume that this quantity, integral between 0 and 1 of max of HIT minus min of HIT dt, this thing is bounded independently of I. Okay? Maybe I should say that I is well, it's a sequence. Okay. Okay. Yeah, it's called finite energy because this quantity, which is really everywhere in symplectic geometry, is sometimes called the energy, the energy of the Hamiltonian, or sometimes it's called also the Hofer norm of the Hamiltonian. Okay, but it's like a very natural norm from the point of, for a symplectic topologist. But I mean, don't worry about the precise definition. It's some kind of C0 norm. Okay. And we set F to be the set of finite energy homeos. Okay. I need to say, so this definition is a variant of a definition which is due to O and Müller from 2006. Okay, some of this definition come from them. And there's an easy proposition, which is almost an exercise too. It's to show that this F is a normal subgroup of G. That's easy. What's difficult is to show that it's not everything. Okay, that's the thing. Okay. And now I'm going to give a candidate for not being finite energy. So we call them infinite twists. So I will consider Hamiltonian. So on the two-sphere, you will use cylindrical coordinates, theta z, and I consider only Hamiltonians which are of the form 1/2 h of z. So a function of the height. H, well, z. Okay. And we assume that h is 0 for negative z, and that, maybe I should say h is defined from -1, 1, but it's not defined up to the North Pole. So this is 1, -1. I do not assume that h is defined at the North Pole. Okay. Okay, but I consider Hamiltonian which is defined this way, except it's not defined at the North Pole. Okay. Then it's easy to write down the time one map of the flow. It will, it follows the level set, so it will turn this way. It preserves all circles. Okay. And we have this formula. Okay, so dynamics is very, very simple.
In the definition of large H,
yes.
Maybe the theta is preserved or something?
Yeah, it doesn't depend on theta. H only depends on the height, on z.
Yeah, but
That's wrong.
small h has a real value.
Yes. Yeah, sorry. Little h is defined on between -1 and 1, so it's defined on the z variable, and then, okay. So the level sets are these horizontal circles. Okay. So we can easily compute the flow. We get this at the time one map. And in fact, we see that it extends to a continuous map to the North Pole. Okay. Extends to an element in G. Okay. And so the difficult lemma was to show that if the integral of h is infinite, then this tau does not belong to F. So it's not finite energy. Okay. So this normal subgroup is proper. So the group is simple. Okay. That's where we are. Any questions so far?
Yes. I have a question about the easy part of the.
Yes.
Why is it a subgroup and why is it not?
Sorry?
Why is it a subgroup and why is it not?
Okay, I can give you some ideas. In fact, there are formulas for compositions of Hamiltonian flows, and so if I have two Hamiltonians H and K, then I may write their composition. It will be given by this formula. Tx. It will be well. I have to. G phi. I think it's this. I'm not sure. Maybe there might be a minus here, but I'm not sure. And then so you have a formula like that. Okay. And from that formula, this generates the composition of the flow. This is an easy exercise. And then from that, you see almost directly that it is stable under composition. Okay, and then you have similar formulas for the inverse, and you also have a formula for conjugation. Okay.
Yeah, but the conjugation, but something which is only continuous.
Yes, but you take. So it is only continuous, but you approximate it by a smooth sequence. Okay, so let me write it. You have so you assume that phi hi 1 converge to psi. That's the assumption. Okay, and then you want to conjugate with some h. I don't know if you can read it. 1 h inverse. This will converge to h psi h inverse, right? And this is also approximately hi phi hi inverse hi inverse. No inverse here. Like that. For some hi which C0 converge to little h. Okay. Here I'm using the fact 2. Where is it? It's here. The fact that it is a C0 closure. Okay. And then this is phi hi composed with h, maybe inverse here. Inverse. And that's it. Okay. Okay. All right. So now I need to talk about impressionistic view of flow homology. So I think that's really something you can learn in finite time, flow homology, but maybe not in 5 minutes. So it's going to be impressionistic. Okay. So we start with some Lagrangian submanifold. I will explain Lagrangian submanifold in the space R2n omega. I'm leaving dimension 2 for a while because I will need to go to higher dimension. Okay. So what does it mean? I'm in R2n, and I'm considering the standard symplectic form in R2n, which is the product, well, not the product, the sum of area form on all R2 factors. Okay, so dx1 wedge dy1, dxn wedge dyn. So it's really like you put an area form on each R2 factor, and you take the sum. Okay. And a Lagrangian submanifold means a submanifold of the dimension n, and such that omega vanishes on L. Okay, so these are really like the most important submanifold in symplectic geometry. And maybe an important example is if you take the product of curves. Then you get a Lagrangian torus in R2n. Okay. So it turns out that when you are in R2n, if you take a Hamiltonian on R2n, you can also associate a vector field as I did here. Okay, you do the same in each factor, basically. And you can also associate a flow phi ht like that. Okay. And you can study the dynamics. I need to erase something. And there's a fundamental fact which is kind of known since several centuries now. There's a function which is defined on the loop space. So omega is closed and exact on the R2n, okay, and I write lambda as a primitive of omega. And I may consider this function, so it goes from the space of paths from L to L, takes values in R, and to a path that we denote x, I'm associating the integral of ht x of t dt minus integral of lambda over x. Okay, this is called the action functional. For every h, we have such thing. And the fundamental fact is that when we consider the critical points of this function on the space of paths, you get exactly the Hamiltonian orbits, the orbits of this vector field xht. Okay, orbits of xht. I mean orbits, since we are restricting the domain of the function to paths from L to L, we get orbits from the Lagrangian to itself. Okay, so chords from the Lagrangian to itself. So that's really the fundamental fact, and that's the starting point of Floer homology. If we want to find such orbits, then we just have to find critical points. Now, if the world was very simple, then our space of paths would be finite dimensional, and we could use Morse theory to find critical points. Okay, because you know there's something called Morse theory. That does a lot of things, but among all these things, it can associate to any given generic function on a finite dimensional manifold. It says that we can recover the homology of the manifold from a chain complex. Which is formally generated by the critical points of the function, generated by critical point of f. Okay, so that's one of the things that Morse theory tells you. And the idea of Floer theory is to adapt this idea from Morse theory to this infinite dimensional setting, where you're not on a finite dimensional manifold, but you're on this space of paths. Okay, and so Floer theory so this is Morse theory in some infinite dimensional situation. So here we will consider a chain complex that is denoted CF star L H. Well, at this point it's just a vector space, which is generated by the critical points of the action functional, or say differently, it's generated by the Hamiltonian orbits from L to L. Okay. On this, it's possible to build a differential. I'm not going to explain that. Yeah. And okay. and we get a homology theory associated to the Lagrangian manifold. Okay, so I didn't put H in the notation for the homology because the homology you get do not depend on H. It only depends on L. And so, in fact, if you start from a Lagrangian in R to N, you will get 0. So it's not very interesting. But this can also be done in other situations. Done in other manifolds, like for instance CPN for some Lagrangians. Okay, and in some cases you get homology which is non-trivial, and the fact that it is non-trivial just tells you that there are Hamiltonian orbits from the Lagrangian to the other, from the Lagrangian to itself. So it has some dynamical, the fact that this homology is non-trivial has some dynamical content, if you wish. Okay. Now we want to somehow extract invariance from this kind of maybe at some point I need to use this. Okay. So now I'm going to tell you when, in which situation, for which Lagrangian I will need to use it for my results. And in fact, we want a Floer theory on symmetric products. Symmetric products. So let me explain. So we are back to S2. Okay. I take some integer which is at least 1, d. Okay. And you know the default symmetric product of S2 is just by definition the product of S2 with itself d times. Okay. Mod out by the action of the symmetric group by switching coordinates, permuting coordinates. Okay. So we consider this quotient like that. Okay. And in fact, it's not too bad. I mean, it looks bad, but it's not too bad because it's it can be identified with the complex projective space of dimension d. Okay. Except that this is just a homeomorphism, and but it's smooth almost everywhere somehow. It's smooth except along the diagonal. Okay, so it's this space is not too bad. Okay, and if you start with an area form on S2, you get a symplectic form on S2 cross S2 cross S2. Okay, which descends to something which will not be smooth everywhere. You'll have to smooth it along the diagonal, but somehow you still get a reasonably good symplectic form on this space. And we can consider also certain Lagrangians constructed this way. So we take D1, D sub D, disjoint disks in S2. So this is S2, and these are just disks. Okay, D1, D2. And we may consider the Lagrangian, which is obtained by taking the product of the boundary of the disk. D1, DDD. And okay. And the fact that the disks are disjoint initially tells you that this product in S2 cross S2 cross S2 will not intersect the diagonal, so it will descend to smooth Lagrangian to the symmetric product. So you get a smooth Lagrangian into in the symmetric product. And somehow the theorem that we proved is that for these for such Lagrangians, it's possible to define. I forgot to say what's H. We take an HT from S2 to R, and then it also induces something like on the symmetric product by taking a sum of HT. Sum of H on each factor. So you get H, I don't know, HT of X1 plus HT of XD descends to something that I will denote sim H. Okay. And so what we prove is that the Floer theory, there's a condition. We need to assume that all disks have the same area. So assume for all I, the area of di is exactly 1 over g plus 1. Somehow it makes a partition into d plus 1 regions of the same area. 1 is the area of the sphere, by assumption. Okay. Then in that case, the Floer homology of the Lagrangian, L, which is defined this way, for this Hamiltonian, is well defined and non-trivial. Okay. And if you think about the meaning of the dynamical meaning of this non-triviality, it's actually something you can probably prove directly without constructing the Floer homology in that case. But it just says that there exists always like a chord in the symmetric product, and a chord in a symmetric product is something like a collection of chords that connects the disk. So you have something like that. Tell you existence of Hamiltonian orbits which permutes the disks like that. Okay. So that's some of the dynamical content of this group. Okay. Okay. So that. Okay, I still have 15 minutes, something like that. And then, what do we do with that? We will define what is called spectral invariance. I have to send it up there. Yeah, homology is not enough. What I want is numerical invariance, so invariant numbers in real numbers. Okay. Otherwise, I won't get a quasimorphism. Okay. And so the idea will be to use Floer homology to capture some critical values of the action functional. Okay. By some min-max. So this is the idea of what is called spectral invariant. So that's a construction which is originally due to, since I'm giving name, I realize I forgot to give name. In this theorem, actually, we proved it, but we are using a lot of ideas from a field called Hegardt-Fleur homology, right? It's really the similar story to what is done in Hegardt-Fleur homology, this symmetric product and considering Lagrangians there. Okay, and these spectral invariants, so they were originally constructed by Viterbo in some very specific case, and then it was extended to some Fleur theories by Young and O, and studied by many authors, and ultimately the version we use is due to Leclerc and Zapolsky. So let me write the definition and then explain. I take a class, the Fleur homology, a Lagrangian, a Hamiltonian, okay, and I will define L of all this data to be the infimum of all real numbers C, such that alpha has a representative sum of ki xi, so that's a chain, okay, with xi being the critical value of the action, okay, and I want that all these critical values are less than C. Okay, so let me explain.
So where does alpha lie?
Yeah, that's one of the things I have to explain. So this belongs to HF. So it's a Fleur homology class, and it's not 0. Okay, so it's alpha will be represented by linear combinations of orbits or linear combination of critical points. Okay, and that's what you see here. And then I want to see the first level C where this class is represented somehow. Okay, so we can make a finite dimensional picture to understand what happens. Let's assume we are not on the space of paths, but we are on the torus, and we are considering a function like that, f. Okay, and we can make the same thing, like we consider a homology class, for example, alpha, the class here. Okay, and we want to find the list C under which alpha is a representative. Okay, and maybe you see that under this level set, alpha is not represented. Right, this homology does not exist below this level set, but it exists right after this level set. So this is the level which is captured by this invariant. Okay, and so we use this simple idea using in the Fleur setting. That's it. Okay, and the good thing is that, I don't know, for example, it's easy to see in that case that when you move f a little bit, then this L will move continuously. So it's a very stable way to capture, and canonical. It's also a canonical way to associate a critical value to Hamiltonian and a Lagrangian. Okay. And so our quasimorphism will be these kind of numbers. Okay. So we let L and L prime be two Lagrangians coming, too many M's, coming from configurations of disks of D and D prime disks. So basically, I'm considering two such Lagrangians. Okay. And I will consider the difference. I picked some classes, alpha prime. It's not really important which one I take. And some Hamiltonian on S2. And we will consider the following quantity, L of alpha L H minus L of alpha prime L prime H prime. Okay. So the point of considering this difference of invariants is that it kills the ambiguity. I mean, H. If you shift H by a constant, you get the same diffeomorphism. So considering a difference of two such invariants kills this ambiguity. Okay. And this I will denote by eta L L prime H. I'm forgetting alpha and alpha prime from the notation. So okay. And I will just give you now the steps of what the different steps that we have to prove our result. So the first step is to show that L, this quantity, in fact, only depends on the time one map. In fact, what the theory gives you is that it depends on the isotopy generated by H only up to homotopy. But then since the group we consider is oh, that doesn't work. Well, maybe at this stage it does. There's a problem. It's only It's only after homogenization that it only depends on the time one map. After homogenization. Okay. And so here we are using the fact that the pi1 of the group is finite. So then, and then another thing we need to prove is that this extends to G. Because a priori, this is just an element in diff S2 area, right? It also extends. So we need to prove some kind of C0 continuity to G. Okay. And for that we use like fragmentations and these kind of things. Okay. We need to show that it is a non-trivial quasimorphism. I will not be able to give ideas for why it is a quasimorphism, but this is a quasimorphism. Eta L prime is a quasimorphism. Sorry?
It is continuous on
different. It's going to be indeed a continuous quasimorphism on G, which is C0 continuous. Okay. And in fact, it does not really depend on the choice of configuration. It only depends on D and D prime. Okay. Only depends on D and D prime. So now my notation will be eta D D prime. Okay. Sorry, there's no prime. It's the same Hamiltonian, sorry. No, if you want to have something that only depends on the time one map, you need to somehow compensate the fact that h is defined only up to constant. Okay, and there would be a way, a natural way would be to consider only the only h which has integral 0. It's sometimes relevant to do that, but for us to achieve C0 continuity, it's really important to not do that. And this is the thing that works. Okay, I'm almost done. Another thing to show is that all the mu d1 are linearly independent. Maybe that's not important for the theorem I stated, in fact, but let's put it as a complement. These things are linearly independent. So in fact, we get an infinite dimensional family of quasimorphism on G. Okay. And okay, so I think. Well, sorry. Mu is eta, yes, that's, no. Mu is eta. Thanks. Okay, and now I should explain why. So the existence of this quasimorphism tells you at least the part that cup length is unbounded, okay? Not cup. Commutator length is unbounded, okay? Now I need to show that this map tau, which is here, is not finite energy. Okay, and for that there are two things to show. First, we show that if phi is finite energy, then these quasimorphisms are the sequence of quasimorphisms is uniformly bounded. Okay, that's where we use this definition of a finite energy. Okay. We need to show that, and then we need to show that we can actually compute these invariants for tau. Okay, and then we show that mu d1 of tau converge to infinity when d goes to infinity. And for that, we really need this condition. Okay, and that this is like just computation. And if you put those two things together, you get that tau does not belong to the subgroup of finite energy homeomorphism, and so you get the non-simplicity. Okay, so I think my time is over, so I will stop here. Thank you very much for attention.